ML stands for machine learning, and DL stands for deep learning. So what we can understand from this is artificial intelligence. It is an approach to mimic the human intelligence. So whenever we want to mimic the human intelligence, or we wish to make computers to think like human being, then we call the broad area as artificial intelligence. In this, we have a subset called machine learning, and then within that you have one more subset which we call it as the deep learning. So it is basically an interdisciplinary discipline. That means it has lot of contributions from computer science, neuroscience, statistics, physics, optimization theory, as well as signal processing. So today we will try to see some of the aspects of signal processing which are related to this machine learning. Then whenever we talk about learning, so how to learn from the data. So that we broadly classify into three different categories, like supervised learning, unsupervised learning, and then when we have reinforced learning. An intersection of all these things, we call it as the machine learning. So later on, you will be learning about what is supervised learning. That means we are trying to learn through data, that is labeled data set. We call it as the supervised learning. In supervised learning, there will be always a reference or the supervisor, that we call it as the supervised learning. If there is no labeled data set, still we want to perform learning, then we call it as the unsupervised learning. All kinds of clustering mechanism comes under the category of unsupervised learning. And if there is some kind of a reward associated with the learning effort, we call it as the reinforcement learning. And the intersection of all this, we call it as the machine learning. Now, the general framework of machine learning. So the general framework, it starts from data. So that data, we call it as the input signal. That signal can be either a one-dimensional signal, or it could be a multidimensional signal. So one-dimensional signal, it could be a speech signal, an ECG signal, or it could be an EEG signal. Similarly, multidimensional signal can be an image or a video, and so on. From the input signal, we want to do some kind of a pre-processing. So the need for doing this pre-processing is to improve the quality of the signal. So if the signal is corrupted by noise, how to do some kind of a filtering so that the signal will be a clean signal before it is being taken to further processing. That aspect we call it as the pre-processing. After pre-processing, it is given to feature extraction. So feature, it defines the data. So how we are able to extract useful information from the data, that is done by means of this feature extraction. This feature extraction, it could be done in spatial domain, or it could be done in transform domain. So spatial domain, we call it as the time domain. Spectral domain, we call it as the transform domain. So once the features are extracted from the input data, naturally it will be fed to the classifier. There are different types of classifiers available, starting from statistical classifier like Bayes classifier, neural network, SVM, random forest, so many type of classifier. For all the classifier, the input will be the feature set and the output will be the class label. So if your computer is capable of learning the feature by itself along with the classification, then that particular domain, we call it as the deep learning. So what we can say is deep learning is basically a subset of machine learning, but it is basically data hungry. Deep learning, that itself, it shows that it is data hungry. Now, what is the data that we are going to feed to the machine learning? We call it as the signal now. So this signal, it is basically a physical quantity which conveys information. In general, it is a function of one or more independent variable. The signal can be thought of as a record of physical activity. For example, record of physical activity of the heart, we call it as ECG signal. Record of physical activity of the brain, we call it as the EEG signal. In general, the signals are analog in nature, but once we want to process the signal, you have to convert that signal into a digital signal through two important phenomena called sampling and quantization. So most of the real world signals are analog in nature. Some of the classic analog signals in real world, that includes temperature, pressure, level, voltage, current, power, and then with respect to mechanical domain, we have acceleration and torque. So all these things are real life signal. Whenever we encounter real life, definitely we cannot get rid of all these physical parameters. These physical parameters, we call it as the signal. For example, if we take human body emits so many types of signals. For example, record of physical activity of the brain, we call it as the EEG signal. It is basically a multi-channel signal where the signals are extracted through electrodes. Now we have PPG signal as well as ECG signal. ECG signal, electrical activity of the heart. Then we have heart sound like lub dub sound, that we call it as the PCG signal, phonocardiogram signal. Then electrical activity of the eye, we call it as the EOG signal. Then electrical activity of the muscle, we call it as electromyogram. Then this broad classification of biomedical signal, it can be given in this called as taxonomy of biomedical signal. First we have bioelectric. Bioelectric stands for ECG, EEG. All these signals come under the classification of bioelectric signal because the output will be in terms of either voltage or current. Then we have bioacoustic signal. Classic examples are heart sound, lung sound. All these things comes under the category of bioacoustic signal. We have biooptic signal. Classic example is PPG, biomagnetic, biomechanical, like blood pressure, airflow, all these things we call it as biomechanical. Then we have biochemical signal and biothermal signal. So you can see that there are wealth of signal that is available from human body. Then these signals we can broadly classify based upon the dimension as well as based upon the nature. Dimension refers to number of independent variables required to convey the information. We call it as dimension. Nature refers to how the signal varies with respect to time or space. For example, with respect to dimension, we can classify the signal as one-dimensional, two-dimensional, and multi-dimensional signal. Based upon the characteristics, we call it as the deterministic or random signal. If we know the knowledge about the signal without any uncertainty, we call it as deterministic. But in real world, always there will be some uncertainty associated with the signal. Hence, it is called as stochastic signal or random signal. Then we have continuous as well as digital. Many signals, if it repeats itself, then it is a periodic. Otherwise, it could be quasi-periodic like your ECG signal. Then you have energy power. Then the last classification is with respect to stationary as well as unstationary signal. That means stationary signal means the statistical characteristics of the signal do not change with respect to time, whereas in non-stationary signal, the statistical characteristics changes with respect to time. Classic example of one-dimensional signal, what we have shown is ECG. For example, in machine learning, nowadays people want to find arrhythmia like bradycardia, tachycardia, such kind of diseases, how we can automatically diagnose from the ECG signal. Nowadays, we are getting this ECG signal through smart devices like smartwatch, everything. They are capable of acquiring the ECG signal. Once the ECG signal is acquired, what kind of diseases that are most likely that can be calculated or it can be estimated from the ECG signal. One such thing is arrhythmia. So arrhythmia detection from the ECG signal. And how to understand the EEG signal. Wherever we talk about EEG signal, we have different rhythms like alpha, beta, theta, delta. These are all the different rhythms that are available in EEG signal. From the EEG signal, we will be able to understand whether the person is awake or the person is in deep sleep and what kind of an emotion that a person has. All these things we will be able to detect from the EEG signal. If there is any kind of seizure that is there in the human brain, that is also possible to detect from the EEG signal, as well as if a person is prone to epilepsy, that is also possible to detect from EEG signal. Nowadays, machine learning and deep learning algorithms, they are widely used to estimate early detection of epilepsy from the EEG signal. Now, two-dimensional signal means there is a variation along X and Y direction. That is what we have to understand from the notion of two-dimensional. classic example of two-dimensional signal are images. So images, visually, it conveys the information, which is what I can say is more appealing when compared to one-dimensional signal. That means an image is worth 1,000 words, or a video is worth 1,000 sentences. These are all classic verbs you can see whenever you learn from the textbook. That means visual information is more powerful than the textual information. With respect to the nature, signal can be either deterministic, periodic or aperiodic, stationary or non-stationary. Based upon this nature, we have to apply different strategies to extract information from the signal. The different parameters of the signal with respect to time domain, we have amplitude ratio, we have duration width, peak amplitude. For example, RR interval in ECG signal, it is one of the good time domain parameter which can be used to estimate the heart rate of the person. Similarly, frequency domain, you have frequency, power spectrum, all these characteristics can be used to detect some kind of diseases that is there in a particular person or not. Other than time and frequency domain, we have also shape features. For example, whenever we do some kind of an automation like grading of tomato or grading of fruits, in that case, shape plays an important role along with color. Shape and color features, they are also equally important features. What are all the different ways by which the signal can be represented? One, by means of a graphical form, functional form, you have tabular form as well as sequential form. So let us try to understand these different types of representation through standard test signals like unit sample, unit step, unit ramp, and then exponential signal. For example, this is the graphical form of del of n, which is unit sample signal, and functional form, this is the tabular form, and then this is the sequential form. So we have 4 different ways to represent the signal. So whichever is more convenient for a particular application, that can be taken into account. Similarly, you have unit step signal, 4 different ways of representation of the unit step signal. Then you have unit ramp signal in this way. So these are all the 4 different forms of representation of the standard test signal. Once we understand the representation, what are all the different mathematical operations that can be performed on the signal? So this slide represents what are all the various mathematical operations. So one mathematical operation could be scaling, next one is folding, then shifting. Whenever we talk about scaling, it can be either amplitude or time scaling. Whenever we talk about time scaling, there are 2 approaches to it. One we call it as downsampling, the other one is called upsampling. So these 2 are very, very important with respect to multi-rate signal processing, how to decrease the sampling rate or how to increase the sampling rate of the signal. So this is represented in this mathematical way. Then shifting means either we can shift the signal towards right or we can shift the signal towards left. One is called the delay, the other one is called as advanced operation. Combining all these things, we have a powerful operation called as convolution. So what is basically convolution? It is basically a mathematical operation which is used to extract information from the signal. So this convolution, it involves 3 powerful mathematical operations with a multiplication, addition, and then delay. This convolution plays a very important role with respect to filtering. Now we will try to understand this convolution through a very simple example. There are 3 different classes of convolution. So today we will try to understand linear convolution. There is also another type of convolution called circular and then section convolution, but we will try to restrict our attention to linear convolution. So our objective is to perform linear convolution between these 2 signals. That is, x of n is 1, 2, 3 and h of n is 1, 1. So this h of n decides the nature of the filtering. That is what we have to understand. So how to perform linear convolution? For example, if we observe h of n, it has got 2 samples, 1, 1. That means we will have 2 multipliers here. So 2 multiplier, one corresponding to this one, the other one corresponding to this one. These 2 multipliers are connected through an adder and they are connected through a delay in the numerator. Now the first sample in the input signal 1 comes here. So since the delay previous element will be 0. If the system is at rest, then once you switch on the system, initially the output will be 0, that is represented like this. So 1 into 1, 1, 0 into 1, 0. So you will be able to get the first output as 1. Now the second sample from the input signal, 2 is coming here. So 1 will be shifted there. So 2 into 1, 2, 1 into 1, 1. So you will be able to get the next sample. Now the next input from the input is 3. That is 3 is coming here. 2 will be shifted there. So 3 into 1, 3, 2 into 1, 2. So you will be able to get a 5. Now there is no more sample in the input signal. So a 0 will be coming here. 3 will be shifted to the relay so that you will be able to get a 3 at the output. So what we want to convey here is the length of the output in general is greater than the length of the two input signal. This is what we have to observe from the linear convolution. The length of the output signal is greater than the length of the input signal, and the nature of the output is purely governed by this h of n. H of n decides the nature of filtering, because this convolution plays a very important role in CNN. So the name itself, it is convolutional neural network. So during that time, we have to understand the operation of convolution. That is the reason why we have given a brief overview of convolution here. Now coming back to signal processing. So first we have talked about signal, various mathematical operations that can be performed on the signal. Next thing is, what is the notion of signal processing? Signal processing basically deals with generation, transformation, extraction, and interpretation of information. Again, it is a multidisciplinary area. So lot of applications are there for the signal processing. One could be filtering of the signal. The other one is enhancement of the signal. For example, how to improve the visual quality of the image. We call it as the enhancement. Then comes the detection, whether a particular disease is present or not. Then where that particular disease is locating, that we call it as localization. Then how to classify, what is the grade of that particular disease, whether it belongs to grade 1, grade 2, grade 3, we call it as the classification. Then another important area in signal processing is prediction, that is predictive data analytics. Nowadays, instead of waiting for the fault to occur, the community, research community is very much interested in predicting when that particular device will fail. That we call it as the predictive data analytics. That means data analytics is the broader term. Within the data analytics, we have a very wonderful area. We call it as the predictive data analytics. And the last area is compression. Since we are living in the world of digital data, how to transfer the data with minimum space as well as with minimum duration, all this technique that comes under the umbrella of compression. That means signal processing involves all these different areas. Now, this is the general flow of the subject. DSP deals with generation, analysis, and processing of the signal. Mostly it deals with deterministic signal, but if we encounter random signal, how to process that signal with uncertainty, statistical tool will come to picture. Statistical tools like we have first order moment, second order moment, higher order moment, and how to deal with non-linearity in the input data. All these things people will learn in advanced signal processing. So in a nutshell, the real world is analog in nature. We want to get the data from the real world and we want to process it by means of a computer. We are in need of A to D converter. Again, we want to take the decision to the real world through D to A converter. Here the processing refers to, it can be filtering, it could be detection, coding, or synthesis. For example, speech synthesis, face recognition, then you have prediction. All those things will come under the umbrella of signal processing. For example, this image, it is corrupted by a Gaussian noise. How to remove this noise so that my image will look better. So if you remove the noise, naturally we will be able to interpret the image in a better way. That we call it as the denoising. Whenever we talk about power line, there are so many types of faults in power line. For example, spike. So this slide shows this power line is affected by spike kind of noise. This is called as sag. Then you have swell. Then you have momentary interruption. So these are all different types of faults. Then this represents some kind of a drift, and then this represents the offset. These are all different types of faults in power line. So how to detect this kind of faults so that I'll be able to get a uninterrupted power supply? All these things are possible through signal processing. Again, without DSP, it is very hard to live because DSP is there everywhere, like your cell phone, there in audio, then in automotive industry, like active suspension, then you have infotainment, in medical field like X-ray, MRI, CT, everywhere one DSP algorithm will be there. So signal processing plays a very, very important role in different aspects of life. So once you define the signal, now the next one is how to process the signal. That means who will be doing the processing. The name that is given to that processing element is system. That means system is capable of extracting useful information from the signal. So this system, it is defined as something which performs meaningful operation on the signal. So what is basically a system? A system is one which performs meaningful operation on the input signal. Mathematically, it is a transformation. So X of n is the input, Y of n is the output of the system. So Y of n is equal to transformed version of X of n. That means it is a transformation. What kind of a transformation we need? Whether we want a linear transformation or a non-linear transformation, all these things you will appreciate in neural network. In neural network, a very, very important function what you will be defining is an activation function. There are different types of activation function. You have tanh, you have sigmoid, you have ReLU, you have leaky ReLU, all those things that basically perform some kind of either a linear transformation or a non-linear transformation. For example, non-linear tanh, sigmoid, ReLU, all those things will perform non-linear transformation. So we have to understand those transformation from the system perspective. This is what the objective is all about. So for any system, you will be giving something as the input that we call it as the excitation. The output is also known as the response. So anything that is fed to the system, I'm calling it as excitation. Anything that comes out of the system, we are calling it as the response. So this excitation, based upon the nature of the excitation, we have different types. For example, based upon application, the system could be either an amplifier or an oscillator or a rectifier or a filter. So all these are fundamental electronic components. Without this, the electronics world will never exist. Then how the system is giving an output to the environment, that we call it as the response. So three different types of responses are there. One we call it as impulse response. Second one we call it as step response, and the third one we used to call it as the frequency response. So based upon the nature of the excitation, the responses are classified into impulse, step, and then frequency response, so that the frequency response is a combination of both magnitude and phase response. This system we can describe in terms of a difference equation. So mathematicians will be really interested in solving the difference equation. For example, if it is a discrete time system, it is a difference equation. If it is a continuous time system, then it is a differential equation. There is a subtle difference between differential equation and a difference equation. For discrete time system, we will be using difference equation. Another terminology is transfer function, pole zero diagram. Then we have frequency response. All these things are basically used to represent the system. So this is the difference equation of a discrete time system, where X of n is the input and Y of n is the output. Transfer function is basically ratio of numerator polynomial to the denominator polynomial. In Z, we call it as the transfer function. Then we have pole zero plot, where cross denotes the pole and circle represents the zero. Then any frequency response is a combination of the magnitude response and the phase response. So we want to understand that system can be represented in different ways. One is by means of difference equation or a transfer function, pole zero diagram, or the frequency response. Now, this system we can classify into different categories. So based upon the nature of the input and output, either it can be an analog system or a digital system, or it could be SISO, single input, single output system, single input, multiple output system, MISO or MIMO system. This system could be a linear or non-linear. For example, whenever you talk about speech processing, people will be interested in extracting the non-linear features of the speech. In that case, we should know something related to non-linear. Most of the cases, it will be time invariant, but in some specific cases, it will be time variant system. Then you have causal, non-causal, stable, as well as invertible system. So this is a broad classification of the system, but we have to understand that system can be defined in terms of the impulse response. So if you know the impulse response, you can know the nature of the system. So this slide explains this. So if your impulse response is 0 for n less than 0, definitely it is a causal system. It is equal to 0 for all n not equal to 0, then it represents a memoryless system. If the system is a stable one, then the impulse response should be absolutely summable. So these are all some of the facts that we have to understand with respect to the system. Once we know the system, then the next immediate thing in signal processing is transform. So always it is better to take the signal to some other domain where we will be able to extract more information from the signal, that we call it as the transform. So transform is basically a different representation of the same signal, where the signal is represented in terms of basis function. Different basis function gives rise to different transform. So the need for transform, it could be explained by a very simple slide like this. For example, you have a prism. We are passing a white light on this prism. We will be able to get a VIBGR at the other end of this prism. This action we call it as the dispersion. So dispersion basically splits white light into its constituent colors. So if there is a white light here, for a person on the other side, it is a combination of 7 colors. That means prism allows this person to extract more information about this white light. Similarly, you have transform. Transform allows us to extract more information from the signal. That is what we have to understand. There are different types of transform. Some transforms are exclusively used for system study, and some transforms are exclusively used for signal study. So these transforms I will be listing one after the other. The most prominent of all transform is the Fourier transform. Then we have Laplace transform in the continuous domain. Then Z transform in the discrete domain. So whatever action that is done by Laplace transform in continuous domain, the same action it will be done by Z transform in the discrete domain. So that is the fundamental difference between Laplace and Z transform. We have two notions. If we want to take the signal from time domain to frequency domain, we call it as the forward transform. Forward transform is also known as analysis. If we want to bring the signal back to time domain, then we are in need of inverse transform. Inverse transform is also known as synthesis. So forward transform is known as analysis, whereas your inverse transform is known as synthesis. So Fourier transform is a very, very prominent transform which was developed by Fourier in the year 1809. So the basic idea is to study the flow of heat through the object. This Fourier transform we can broadly classify into 4 types, like continuous time Fourier transform, discrete time Fourier transform, discrete Fourier transform, and fast Fourier transform. So these are all different versions of the same idea. That's all. So idea is very simple. We want to take the signal from time domain to frequency domain. So I will give you the brief explanation rather than getting into the complex mathematics. So here forward transform, this is the idea. That means whatever we are getting it here, we call it as the spectrum. Whatever here, we call it as the signal. So signal is in time domain means n. N represents the time index, k represents the frequency index, and this represents the basis function. So transform can be viewed as projecting the signal into the basis function. So it is basically a projection or taking the inner product of the signal with the basis function. You have fixed basis. In transform, that is Fourier transform, the basis function is fixed, which is basically a complex exponential. So e power minus j 2 pi by nk represents the complex exponential. So this x of n represents the signal, this represents the basis. So projecting a signal into the basis function, it will give you the spectrum. Now the reverse of this, we call it as the inverse transform. So a very simple example of DFT and what is its role that we will try to see in this class. So first you have a signal where your input is all 1. For example, 1, 1, 1, 1. If all your input is 1, then you can see that if you compute DFT, the answer is 4 followed by 3, 0. Now, if you try to plot the signal as well as the spectrum, it will be like this. You can see that x of n is the signal which has 4 ones, 1, 1, 1, 1. If you take the spectrum, it is only one sample, remaining all the samples are 0. That means if you have a DC signal, all your signal energy will be packed to DC coefficient, remaining all the coefficients will be 0. This we call it as the sparse representation of the signal. What do you mean by sparse? I am able to represent the signal with only one sample instead of so many samples in the time domain. That means this DC signal is sparse in the Fourier domain. This is what we have to understand from the signal representation. So in time domain, the signal is not sparse, whereas in frequency domain, that is by taking Fourier transform, the signal is sparse. That means I need only one coefficient to represent this entire information rather than all the values. So this we call it as the sparse representation. This sparse representation, it plays a very, very important role. How to develop the dictionary. So how to understand in which domain the signal is sparse. That itself is a challenging task. So in some cases, the signal will be sparse in Fourier domain. In some other cases, the signal will be sparse in wavelet domain. In some other cases, the signal will be sparse in some other domain. So first, our duty is to identify the domain in which the signal is sparse, and then we have to take into account the advantage of going for the sparse representation. Sparse representation means few coefficients will be required to represent the entire signal. That is the main idea behind sparse representation, which plays a very, very important role in machine and deep learning algorithms. So now if you have an AC signal 1 minus 1, 1 minus 1, then again you can see that the signal is varying continuously, but you have only one coefficient here. That means the signal is sparse in the Fourier domain. Even though it is an AC signal, you need only one coefficient in the Fourier domain to represent the variation in the input signal. So sparse representation, it can be done through transform. Next, computationally, your Fourier transform is too intense. In order to minimize the computational complexity, people have started using fast Fourier transform, which is basically computationally efficient form of discrete Fourier transform. There are different approaches to do computationally efficient Fourier transform. This we call it as DIT, DIF, and so many things. But our objective is, if you have a signal, if you take Fourier transform, what is that you will be able to get? So you will be able to get two important information. One is the magnitude information, the other one is the phase information. Using this magnitude and phase, how we can manipulate the signal information. That is the fundamental goal. For example, here you can see that this is a 5 Hz signal. It is basically a sine wave, but in the Fourier domain, you have only one peak. That one peak corresponds to 5 Hz. That means here the signal is extending from 0 to 1. So in this way, but in your spectrum, it is having only one peak. That means this one peak shows that it is a 5 Hz sinusoidal signal. This we call it as the line spectrum. If your signal is a periodic signal, if it is repeating in a sinusoidal way, then your spectrum, you will be able to get a line spectrum. That means you will have only one line to represent this variation. Then if you have a 10 Hz sinusoidal signal, then if it is a single-sided spectrum, then I will have only one peak corresponding to 10 Hz. Anything to be discussed? Any doubt? Shall I proceed? Thank you.
Yes, sir. Yes, sir. Yes, sir.
Okay. The major drawback of this Fourier transform is if there is any discontinuity, the Fourier transform may not be able to capture the discontinuity. For example, you have a non-stationary signal here. That means a slow variation and a fast variation. You have a spectrum like this. If I interchange the fast and slow variation, again my spectrum looks alike. That means it is not capable of providing the time information. At what time that particular variation occurred, I may not be able to find out from the Fourier spectrum. In order to overcome this drawback, people started developing short-time Fourier transform, which is also known as spectrogram. So STFT is basically a windowed Fourier transform where a window will be sliding over the signal, and then we will be able to take a specific part of the signal. For that specific part, we will be taking the Fourier transform. So the objective here is I will be slicing the signal first. How I will be slicing the signal? Using the window. So the window is used to slice the signal. For the sliced part, we will be taking the Fourier transform, that we call it as the windowed Fourier transform. So the resolution naturally it depends on the size of the window. Now you can see that this is a slow variation, this is a fast variation. Now fast variation comes first, slow variation comes next. That means signal 1 and signal 2 are different, but my Fourier spectrum remains the same. But if you take short time Fourier transform, you will be able to observe that slow variation comes first, fast variation comes next. Here, fast variation comes first, slow variation comes next. That means in short time Fourier transform, you have both time as well as frequency variable. That means one dimension and converting into a two dimension through short time Fourier transform. So short time Fourier transform is basically a two-dimensional representation of a one-dimensional signal. So the impact of this window means whenever you are using a shorter window, it will give very good time resolution. If you are using a wider window, it will give very good frequency resolution. Is there any way to get both good time as well as frequency resolution? Immediately that will come to our mind. It is very, very difficult. That answer to that question, it was given by Heisenberg, which is called as Heisenberg uncertainty principle. It is very difficult to get both good time resolution as well as good frequency resolution. For example, here there is only one sudden change. I may need of a shorter window to capture this information. Here the signal extends from this to this. I may need of a wider window to know this signal. That means based upon the scenario, you have to use either a shorter window or a wider window. So shorter window gives good time resolution, whereas wider window gives good frequency resolution. That means if you increase the length of the window, here you don't get any frequency information, whereas here for this signal, if you increase the window length to 128, you will be able to observe that it is a 10 Hz signal. You can see that there is a horizontal line here that corresponds to 10 Hz. That means it is a 10 Hz sinusoidal signal. So if you have a sinusoidal signal, your window length has to be long. If you have a drastically varying signal, your window length has to be short. This is what we have to understand. Now, in Fourier transform, the decomposition, you will be able to get only frequency information, whereas in short time Fourier transform, you will be able to get both time as well as frequency information. The basis function of Fourier transform is a complex exponential, whereas basis function of your STFT is a windowed basis function. The information what you will be able to get in Fourier transform is only frequency information, whereas in STFT you will be able to get both time and frequency information. This Fourier transform is suitable for stationary signal, whereas where STFT is suitable for both stationary as well as non-stationary signal. So this is what transform is all about. But the advanced version of transform what you have is a wavelet transform, which has the ability to perform multi-resolution analysis. Now we will try to give a brief overview about the filters, because convolution basically performs the filtering operation. So we will try to understand filters, then we will go to imaging example. Why do we need filters in signal processing? Filters, basically it performs some kind of a mathematical operation on the signal. That mathematical operation is performed either to confine the signal into a particular frequency band, or to decompose the signal into different frequency band, or to remove the noise that is present in the signal. For all this purpose, filters will be used. For example, in this case, if we are having your input signal like this, it has got low frequency as well as high frequency part. If you pass it through a low pass filter, naturally high frequency component will be eliminated. That means in your input signal you will have two peak, whereas your output signal you have only one peak corresponding to low frequency. That means this filter is able to confine the signal to low frequency range. That is the action of low pass filter. Otherwise, we can divide the signal into low and high frequency region, that we call it as signal decomposition. Decomposition means splitting. This is what we have to understand. Now, if you do low pass filtering, your square wave will turn out to be a triangular wave. If you do high pass filtering, you will be able to know where exactly the change has occurred. What we have to understand is low pass filter will perform smoothing operation, high pass filter will perform sharpening operation. So if I want to put it in a nutshell, whenever we want to do smoothing operation, we have to go for low pass filter. Whenever we want to do sharpening operation, we have to go for a high pass filter. This filter, there are so many categories available, but we will be mainly concentrating on digital filter. Digital filter, there are two categories like FIR and IIR filter. Then you have linear and non-linear filter. Then you have adaptive filter. So these are all different classes of filters that are available. So if we consider an FIR filter, this is the mathematical equation. So this we call it as the difference equation. You can see that n minus k, it is basically a difference operation. So this is the fundamental equation of a FIR filter, whereas your current output y of n depends on the current input and the past input. That is the meaning of this FIR filter. That means current output y of n depends on current input x of n and the past input. It will not depend on past output, whereas it will depend on past input. So this is the fundamental way to understand this FIR filter. Here this B0, B1, B2 are called as the coefficient of the filter. If you carefully observe, I am multiplying my signal sample with the filter coefficient. This filter coefficient decides the nature of the filtering. For example, a very simple 3-point moving average filter, it is given as 1 by 3, 1 by 3, 1 by 3. Whereas a 5-point moving average filter is like this. Let us try to understand the working by a very simple numerical example. Here you have your input signal like this. Can anyone say what is that you can understand from this signal? Just see the signal sample value, which is 9, 6, 102, 3, 6 and 9. Can anyone say what is that you can interpret from this input signal? Anything different? Any idea? Yes, exactly. That is, one value drastically changes from its neighboring value. For example, 102, the neighbor values are 6 and 3, whereas this sample value is 102. That means this value is large when compared to its neighbor. This is what we can understand from this. If you try to pass it through a 3-point moving average filter, your output will be like this. So you can see that these sample values are multiplied and then it is added in order to get the result, so that this 102 turns out to be 37, this 3 turns out to be 37, so 6 and then 5. That means a drastic value, it will be smoothened out by this averaging filter. So this we call it as the moving average filter. if we extend it to 2-dimension, it will be a matrix. It is a 3x3 matrix. Like all the values are 1, 1, 1. So if you normalize it, you have to divide it by 9. So this forms the kernel in convolution neural network. This you will be learning by the name kernel, filter kernel, like that. This is the filter kernel. So if you have a sudden change in the input signal, if you want to minimize the sudden change, this moving average filter plays a very, very important role. So that is the fundamental idea behind filtering operation. So whenever you want to reduce drastic variation in the input signal, you have to go for a filter. There are two classes of filters available. One is FIR and another one is IIR. So we won't get into the detail because so many things have to be discussed. So I'm going to give you a very brief overview of the filter. That's all. So among the two classes, FIR filter is more prominent when compared to IIR filter because of two reasons. One is it is inherently stable, and then it has the ability to provide linear phase response. So there are 4 different categories of FIR filter, like type 1, type 2, type 3, and type 4. So in depth, you will be learning it in signal processing. Time being, I'm just giving you an overview. That means there are 4 different classes of FIR filter, but the main advantage of FIR filter is it is inherently stable and it will provide linear phase response. Out of this, there are 3 different ways to design it. One is window based, frequency sampling based, and then optimal. So IIR filter, even though it is not widely used, still some people have approached it in literature. So IIR stands for infinite impulse response filter. These are all the design criteria. So just time being, I'm not discussing this, but we have to understand that there are 4 different categories like Butterworth, Chebyshev, inverse Chebyshev, and then elliptic filter. Now we will go for a brief comparison. So whenever you talk about FIR filter, the coefficients will be symmetric in nature, whereas the symmetricity you cannot expect in IIR filter. FIR filter exhibits linear phase characteristics. They are inherently stable, and the group delay is constant in FIR filter, whereas it is not constant in IIR filter. But if you want to realize it, you are in need of more number of coefficients. That is the reason why sometimes people are going for IIR filter. That is, we are in need of more number of coefficients to meet the given specification, but you can pay that in order to get an inherently stable filter which exhibits linear phase characteristics. So out of these two, FIR will be widely used. There is again a different class of filter called as adaptive. Adaptiveness means adjusting to the environment. We call it as the adaptive. So filter with self-tuning characteristics, we call it as the adaptive filter. Mostly they are nonlinear filter and then time varying filter. Classic example of this, you have Kalman filter, then you have particle filter. All those things comes under adaptive filter. This is the fundamental block diagram of the adaptive filter. That means the backbone of this adaptive filter is the adaptive algorithm. This adaptive algorithm takes the input signal, the error signal, and then it tunes the filter in order to get the output. This is the fundamental idea behind neural network. So neural network, it basically works like this. So we have an algorithm. That algorithm is basically used to modify the filter coefficient. That modification, we call it as the learning. How much I am learning, that is done by iterations. Whether I need 5 iterations to need proper learning, or I need 100 iterations to need proper learning. Those things, that means always it depends on the error. You can see that I'm comparing my desired signal with the output of the filter, and the error is fed to the adaptive algorithm. The magnitude of the error decides whether the filter coefficients have to be tuned or not. This is the fundamental idea behind adaptive filter. This adaptive filter forms the basis of the neural network. That neural network forms the basis of your AI, machine learning, as well as deep learning. So the fundamental idea is this. There are 2 broad adaptive algorithms. One we call it as LMS algorithm. The other one is RLS algorithm. least mean square error algorithm, recursive least square algorithm. So these two are called as LMS and RLS, etc. The fundamental idea behind these two algorithms is new weight is equal to old weight plus correction term. That correction term depends on the magnitude of the error. So this is similar to that of learning. So my new weight will be always equal to old weight plus correction term. This is the fundamental idea used in adaptive. This is widely used in system identification. So what is basically system identification? You can understand by this. I have an unknown system. I have an adaptive filter. Both are operating in parallel. For the unknown system also, I am giving same signal. For the known system, I am giving the same signal. Whenever the error is 0, what I can understand is this system is mimicking this system. So this is a classic way of understanding an unknown system. So how I am doing? By making this system to mimic like this system, I am able to know what this system is all about. That is called as system identification. It plays a very, very important role in control algorithm. So in this DSP, it finds applications in different areas of engineering like electrical engineering, computer science, biomedical, civil, medical, and so many. In electrical, you have power line signal analysis, fault detection in motor that we call this signature analysis. So from the data extracted from the motor, I will be able to predict the life of the motor. Then it becomes predictive data analytics. Then in consumer electronics, multimedia, this DSP plays an important role. Biomedical signal as well as image analysis, structural health monitoring system, then seismic data analysis. In mechanical, vibration analysis. It plays a very, very important role in order to provide active suspension. For example, there are two ways to travel from one area to another area. If you travel by one bus and the same journey, if you travel through Volvo bus, you will know the difference between these two journeys. For example, if you are traveling by an ordinary bus, naturally more vibrations and the suspension will be there. We will be getting tired. On the other hand, if you are traveling by a Volvo bus, because of the active suspension, you won't feel that much tired. That means that active suspension plays a very important in performing the smooth journey from one place to another place. This signal processing, it has its own impact in speech processing. For example, in speech processing, from the portion of the speech that is given to you, is it possible to find who is speaking, whether it is a male or a female? That we call it as the gender identification. What is the emotion of that particular speaker, whether he is in a joyful mood or whether he is sorrow or he is anxiety. All those things we call it as the emotion recognition. Then speech recognition, how to synthesize the speech. Then natural language processing. All those things comes under the area of speech processing. Another important area, as I've already mentioned, is predictive data analytics. This is the chain of workflow with respect to predictive data analytics. You have set of data. From the data, you want to detect whether any particular type of noise or some kind of an error has occurred. Then you are going for the diagnosis, which is responsible for that error. Then prognosis, how to do maintenance, we call it as prognosis, and then analyze all these things in order to go for a cost benefit analysis. So this is the general flow with respect to predictive data analytics. Now, what is the latest trend in machine learning? For example, you have a speech signal. Directly, you cannot feed that speech signal to a convolutional neural network, because convolutional neural network, it is more comfortable if you feed an image data rather than a one-dimensional data. So the general approach is like this. You have a one-dimensional signal. This could be a speech signal, or this could be a vibration, or this could be an ECG, or anything that we call it as the one-dimensional signal. One way to obtain a two-dimensional signal from this one dimension is partition the signal. For example, I'm doing a partitioning like this, and then I'm taking it to a matrix. I'm doing a normalization. I'm able to convert that one-dimensional into a two-dimensional representation. This is one way to do it. This is not the only way. This is one way to convert a one-dimensional to a two-dimensional representation. Once you are able to get the data in the form of a matrix, very conveniently you can feed it to a CNN or any kind of advanced deep neural network so that you will be able to classify the data. You will be able to do some kind of a regression analysis, whatever you want to do, comfortably you can do it. So the objective is how to move from one domain to two dimension. That means you are going from a smaller dimension to a higher dimension. Earlier, people were talking about dimensionality reduction. Nowadays, people want to go from a lower dimension to a higher dimension rather of dimensionality reduction. What are all the different approaches that can be used to project the data to a higher dimension? For example, I have an one-dimensional data. I want to convert into a two-dimension. So what are all the different possible ways by which I can do it? One way is go for short-time Fourier transform. That means you partition the data through a window and then you take the Fourier transform of the corresponding window that we call it as STFT. The second approach, you can go for Wigner-Valley distribution, wavelet transform. All these things will be able to switch from one-dimensional representation to a two-dimensional representation. Nowadays, empirical wavelet transform also plays a very important role in converting the one-dimensional representation to a two-dimensional representation. So, want to get an overall view about different types of techniques. These are all the fundamental books. So once we are done with this, then a brief introduction to signal processing will be over. Then slightly we will turn our attention to higher dimension, that means two-dimensional data, which is basically images. So if you have any doubt in between, feel free to discuss with me. Anything to be discussed till now? Whatever concepts we have discussed, any difficulty or anything to be clarified or anything to be debated upon, definitely we can do it now. Am I audible, sir?
Yes, sir. Yes. So I think we can have a break after the discussion for 2 minutes. So participants can interact with the resource person, Esakiraja sir. He is very happy to answer your queries this time. Please, you can unmute and speak.
Otherwise, shall we go for the break, sir? After the break, if they have any doubt, then also they can discuss.
Yes,
they can send mail, whichever way the participants are comfortable with. We will go with that way. So now we have given a brief idea about one dimension. After the break, straight away we will start with two dimension and how to link the two-dimensional data to machine learning and what are all the challenges involved in that. We will try to do it in the second session.
Okay, sir. Thank you, sir.
At what time shall we start, sir?
We'll give 10 minutes break, sir.
Sure, sir. Shall we start? Shall we assemble by 11:45, sir? Now it is 11:40.
Yeah.
Shall we start by 11:45 or some more
With
time?
11:50 we can start. So
11:50.
Yeah.
Sure, sir. We will start by 11:50, sir. Thank you.
Okay. So all the participants, we can take a break now. So we reassemble again at 11:50. So thank you, sir. Thank you all participants.
Thank you, sir. Thank you.
Thank you.
Hello, sir. Am I audible, sir? Sir, can you make me the host so that I can share the PPT? Am I audible, sir? Sure, sir. So welcome back. So in this particular session, we will talk about two-dimensional data rather than a one-dimensional data. These are all the topics of presentation. So first we will learn about the basics of image processing, then different areas of image processing, and what are all the research activities that we have initiated from our end related to machine and deep learning that we will try to give us two case studies. With that, we will try to conclude this session. So first, image, it is basically a multidimensional signal. The general representation is in the form of a matrix. Matrix, as we know, it is a intersection of row with the column, that we call it as the most fundamental building block of any digital image, which is a pixel. Pixel stands for picture element, that is the building block of the digital image. Each pixel will have a location and a value. The value taken by the pixel in general termed as the gray level. This is the natural image which is being projected into a grid of numbers. So we are converting a visual information into a numerical number. This we call it as the image. So this image, we have a pixel. The pixel will have a location and the value. The value, if it is an 8-bit image, it varies between 0 to 255, where 0 corresponds to black and 255 corresponds to white. Image is basically formed because of light falling on the object and the light being reflected by the object. That is, f of xy is equal to I of xy into r of xy. So based upon the nature of the incident light, we have either X-ray or visible image, infrared image, or ultrasound, or we have satellite images. Three broad categories of images are RGB, grayscale, and then black and white image. So this is the brief classification of image type, that is RGB. There are different types of color space. Here it is an RGB image. Then we have grayscale and we have black and white. Anything to be discussed? Audible, sir? Okay. Okay, thank you. So RGB images, we have 8 bits to represent the color information, red, green, and then blue. In general, we will be in need of 24 bits to represent the RGB image, 8 bits to represent the grayscale image like this, whereas only either 0 or 1 is used to represent the binary image. We have three different types of resolution. One is grayscale resolution, another one is temporal resolution, then we have spatial resolution. There are three broad resolution. First, we will talk about spatial. We'll go to gray level. Then with respect to video, we have temporal resolution. So spatial resolution is governed by the density of the pixel. This is an image with only 3 megapixel. This is an image with 1 gigapixel. That means with increase in the density of the pixel, the clarity of the image looks good. With the value taken by the pixel, the spatial resolution is being different. Now, the gray level resolution with a different bit budget is shown in this particular diagram. So, if your bit budget is low, the clarity of the image is poor. If your bit budget is more, the clarity of the image will be better. Different file formats through which the images are stored are JPG, PNG, and then BMP. Then simple examples, it refers to enhancement. So image on the left hand side, definitely the contrast is poor. That is the reason why the clarity is not good. Whereas the image on the right hand side, the contrast is good. That is the reason why the visual quality seems to be better. Now you have this retinal image here on the left hand side, the clarity is poor. If you increase the contrast, naturally the clarity will be better. Similarly, this image on the left, it is suffered due to some kind of a smoothing effect. We call it as blurring. So if we try to pass this signal or this image through some kind of a restoration action, so that we will be able to get the deblurred image. Now, this image is affected by salt and pepper noise. If you pass it through a nonlinear filter like a median filter, you will be able to remove noise from this image. Then if you have an image with low spatial resolution, if you perform interpolation, you will be able to get a better resolution image. So this we call it as the image super resolution. Now, if you have this image here, this big clock, the clarity is poor. Here in this small clock, the clarity is poor. So if you fuse these two images together, so that you'll be able to get a better image, this we call it as the fusion. There are different areas of image processing like image transform, image enhancement, denoising, restoration, compression, morphological image processing, and other image processing. So these are all different areas of image processing, but we try to pay more attention to this segmentation, denoising towards this machine learning and then deep. So in order to do all these tasks, we should have a very good understanding of the mathematical representation of the image. Sir, I think there is a slight background noise or something. Shall we start, sir? Sure, sir. Thank you, sir. So, general representation of a two-dimensional data. So, we will start with a very, very fundamental two-dimensional signal, which is a unit delta signal or unit sample signal. This signal will have a value of 1 exactly at the origin. This signal plays a very, very important role in convolution. That is the reason why we have to understand the notion of the signal. See, N1 is one independent variable, N2 is another independent variable. So whenever N1 is equal to 0 and N2 equal to 0, you will have a value of 1 that is being represented here. On the other hand, if n1 minus 1 equal to 0, that means whenever n1 is equal to 1 and n2 is equal to 0, you will have this. Now you can see that this dot is moving towards right. This we call it as the shifting operation, shifting towards right. Now if you see this, the other way to do it, that is shifting towards left, that is n1 plus 1. On the other hand, if you do along the y-axis, that is n2 axis, then you will have like this. Along n2 axis, if you go along this way, then it becomes n2 plus 1. Then if you do it in both the axes, that is n1 equal to 1 and n2 equal to 1, then you will be in the first quadrant exactly at this point. You see here, this is the point, then it is moving towards the first quadrant 1, 1. On the other hand, if this is the signal, then you will be going to this. That means n1 equal to minus 1 and n2 equal to plus 1. The other way to go around the third quadrant is this. For the fourth quadrant, it will be like this. That means your n1 is positive, your n2 is negative. So these are all different images they can create because of the shifting of the particular pixel value. This is what we have to understand. So del of n1 means n2 axis will be 0, n2 will be 0, so that you will be able to get an impulse. This is the impulse in the other way. The impulse in this direction, n1 equal to n2 means 1, 1, 2, 2, minus 1, minus 1. That means whenever n1 equal to n2, you will have a value of 1. The other way to get is in this direction. This we call it as the line impulse. Two-dimensional unit step signal is, it will be like this. That means whenever n1 is greater than 0 and n2 is greater than 0, you'll be getting it like this. But separable signal, can you see that? This is u of n1, this is u of n2. So the fundamental difference here is u of n1 means all n1 is taking positive value. Your n1 will not take negative value. Here all n2 is taking positive value. So if you multiply these two together, you will be able to get u of n1 n2. That means multiplication of two one-dimensional signal, if it results in a two-dimensional signal, then it is called as the separable signal. It plays a very important role in image processing. So how to get a two-dimensional data from two one-dimensional data is called as separability. Another important operation in image processing is convolution. So what is two-dimensional convolution? We will try to illustrate by a simple example. One-dimensional convolution in the previous session we have discussed. Similarly, two-dimensional convolution we will try to discuss. As such, you can see that 50 is the odd man out because the value 50 is far away greater than the neighboring pixel. Neighboring pixel are mostly single digit. Maximum value is 11. But this 50 is mostly different from its neighbors. See here, 8 neighbors are there. All the 8 neighbors of this 50 are taking small value. Unfortunately, this 50 is a huge value. Now, how to reduce this value by a box filter? That is the idea. This is your original image. This is the filter kernel or the mask that I want to apply it to the image. That idea we call it as convolution or spatial filtering. So the first step is zero padding. So how this zero padding is done? Like this. So this image which will be surrounded by 0, this we call it as the zero padding. Once you do zero padding, then the next thing is apply the mask over the image. See here, this is the mask. This mask I am applying it over the image so that this 7, it will be replaced by 0 into 1 by 9, 0 into 1 by 9. I can see this result, 7 into 1 by 9, 9 into 1 by 9. All these things, it will be added up so that the 7 value turns out to be 8.4. Now this mask will be moved over the image to the right and this value will be modified as 10.7. That means 9 changes to 10.7. Then it will be moved towards right one more time and all these operations happens in order to convert this. Now we are bringing the mask down and then we are doing this processing subsequently in order to modify 50 as 12.9. So 50 is a huge value, whereas your 13 is almost a very simple value when compared to the large value. That means whenever you do this we call it as the smoothing effect. So if you have one pixel which is drastically different from the neighboring pixel, this 50 is drastically different by the neighboring pixel. So if you want to do it, you have to go for a low pass filter. Now you see that this is the image before filtering. This is the image after filtering. That means whenever you do convolution through a low pass filter, you can reduce this value 50 to 13, which is almost closer to its surrounding. So if you have a drastic variation, you don't want the drastic variation to happen, you have to pass it through a low pass filter. That is the learning or the convolution operation that we have learned now. Now, similar to one-dimensional transform, there is a two-dimensional transform. Again, the fundamental idea remains the same. We want to take the signal from one domain through another domain through the basis function. Now, you have forward transform called analysis to take the signal from spatial domain to frequency domain, and inverse transform called the synthesis to take the signal back from frequency domain to spatial domain. So now instead of time, we are using a term called spatial. That is the fundamental difference between this. This image transform, there are so many categories like Fourier transform, discrete cosine transform, then you have Haar, Hadamard, Radon transform. Again, it is a classic transform for projection. All your CT scan, they are based on this radon transform. Medical imaging, this radon plays an important role. So if we take Fourier transform, again, it plays a very important role in converting the time domain to frequency domain. Here we are extending it to two dimension. This is a one-dimensional transform. Just we are extending it to two dimension. So if we extend it to two dimension, what will happen? So this is the simple image that I have taken. For that, if you apply the transform, you can see that all these values, now it is mapped to 16 followed by 0. That means sparse representation you are able to get if your image is basically a low frequency image. That means if you have a DC signal, if you pass it through Fourier transform, here you will be able to get the sparse representation. So how to identify the sparse representation? That is the challenging task in image processing. So because of separable property, you will be able to do it along row, that is like this, and then you will be able to do it along column, so that you will be able to get the two-dimensional representation. Now if you say take the image like this, if you take the Fourier transform, your spectrum will be like this. If I increase the size, you see here small square being changed to a big square, but here you can see that here the dot size will be reduced. That means the expansion in one domain, it is equal to compression in the other domain. Now you can see that I'm having a slit-like structure, SLIT, slit. It is a very common term in physics. For this slit, vertical slit, your spectrum is like this. If I translate the slit, your spectrum will also be rotated. That means rotation of the signal will result in rotation of the spectrum. Now, for what purpose we will be using the Fourier transform? One purpose is filtering of the image. So how I can filter the image? First, you have an image, you are taking the Fourier transform, and then you are modifying the Fourier transform by the filter mask in order to get the filtering operation. So how it is done? A very simple example like this. So here you have a low pass filter mask, so that you can see the images are like this. It will be blurred. Whenever you pass the image through a low pass filter, you will be able to get the blurring action. So your result will be a blurred image. On the other hand, if you do this, that means you are allowing only few Fourier coefficient, the image looks more blurry. If you do high pass filtering, you can see that this is the nature. You will be able to extract the edges in the input image. You can see exactly here. You can see that you will be able to extract the edges in the input image. That means Fourier transform can be used to extract the edge information from the input image. The other one application of the Fourier transform is Fourier transform can be used to identify the periodic noise that is present in the image. Can you see this image? It is basically an X-ray image. If you take the power spectrum of this X-ray image, how will it look like? This is what we want to understand. Now, this is where X-ray image. This X-ray image is corrupted by a sinusoidal interference. So here sinusoidal interference, the frequency is less. Here the frequency is more. Now, how to know what is the frequency of this sinusoidal pattern? Your Fourier transform will give an answer to this question. For example, if you have a clean image, if you take the power spectral density, you can see that there is a white spot in the middle. Whereas, if you corrupt the image by a sinusoidal interference, you can see that along with the central bright spot, you will have additional 2 spots here. The additional 2 spots indicate that this signal is being corrupted by a sinusoidal interference. In the spectral domain, if you erase these 2 white spots and if you take the inverse Fourier transform, it is called as notch filtering. That means you are taking the signal to the transform domain. In the transform domain, you are rubbing these 2 bright spots so that you will be able to get back your original signal. This is called as denoising of the signal. Now you can see this very clearly here. This is the original signal. Now the positions are wide apart. If you can rub these 2 spots, you will be able to get your original signal. So this idea we used to call it as the notch filtering of the input image. But whenever you take Fourier transform, you will be able to get 2 important information. One we call it as the magnitude information. The other one is the phase information. Both are equally important in order to get the image. So this idea is well known by giving a very simple example. For example, this is the cameraman image. This is the Elena image. If you interchange the phase of these 2 images, then this image will look like this. Then this image will look like this. So this we call it as the phase interchange. This phase information plays a very important role in phase recognition. Nowadays, the challenging task is whether a particular phase is present or not. That we call it as phase recognition. So many algorithms are there for phase recognition, like Viola-Jones algorithm, YOLO algorithm, YOLO V3, YOLO V5, like that. In that, if you want to do it in a very simple way, your face can be used as one of the features in order to identify whether the face belongs to a particular person or not. But the major drawback of this Fourier transform is it is complex in nature. So people have gone for other type of transforms like cosine as well as wavelet transform in order to handle this drawback. So if you want to get real numbers from real input, discrete cosine transform is a very important tool which was developed by Ahmad Rao and Natarajan, which is widely used in compression application. Now, other than compression, what is the role of this transform is denoising. Now you can see that here we have 2 dots, one corresponding to green, the other one corresponding to red. Whether the 2 dots are visible? Any difficulty? So the green corresponds to the signal and the red corresponds to the noise. Now the noise is embedded in the signal. Now I want to separate the green from the red. So how to separate these 2 like this? So this is what SVM is also planning. So by taking the data to a higher dimension, is it possible to separate these 2 data into 2 different classes? That is the ultimate objective, but that can be done through transform. See how it is done. It is given by a very simple example. Now you see that this is the shirt. Shirt is my green dot. Your dirt is the red dot. Now the dirt is embedded in the shirt. Now I want to remove this dirt from the shirt. That idea we call it as the washing. So in washing, what is the first step? We will be soaking this cloth in a water and then we will be rubbing it and then we will be drying it in order to get the clean image. Is it right? This is the general step of washing. Now, similar to this, see here, if I want to remove this noise from this shirt, I want to take the shirt from air medium to water medium. Taking the signal from air medium to water medium is transform. Here I have different varieties of water like hard water, soft water, hot water, cold water, like that. Different types of water corresponds to different types of transform like Fourier transform, wavelet transform, cosine transform, like that. Then you have a rubbing action that we call it as the thresholding operation. There are hard rubbing as well as soft rubbing, like that. We have so many different types of threshold. But after washing, straight away I cannot wear my shirt. I want to dry it, then only I can wear it. So drying is called as inverse transform. Soaking is forward transform. Drying is inverse transform. In between soaking and drying, I have rubbing. That rubbing action we call it as the thresholding operation. Now you see here a little bit of analogy. Now this is that you will be able to see. This is the forward transform. So forward transform is like taking the shirt from air to water. Then here you are doing that brushing and then you are drying it. That we call it as inverse transform. So forward transform, wavelet, then rubbing action threshold followed by inverse transform. You will be able to get the nice result. Any difficulty till here? Now, how this image processing can be related to this machine learning. So first case study, what we did in our lab is retinal image analysis. You know that retinal images play a very, very important role in the detection of two important diseases in human eye. One we used to call it as glaucoma, the other one we used to call it as DR. DR stands for diabetic retinopathy and glaucoma. Glaucoma is basically due to pressure variation in the eye, and the diabetic retinopathy causes degradation of the vision. Both are equally a potential threat for the loss of vision. So how I can detect the occurrence of glaucoma or diabetic retinopathy from the retinal images? This is the case study that we have carried out in our research, which fetched one of the PhD degree for our research scholar. The idea here is we are taking the fundus image and then we are pre-processing the fundus images. We are extracting the feature from the fundus images and then we are doing the ranking of the feature. Then from the ranking, we are selecting specific feature and then we are going for classification, whether it belongs to a normal eye or eye affected by glaucoma or diabetic retinopathy. See, these steps we call it as machine learning. So the pre-processing is used to improve the quality of the image. So many types of features can be extracted from the image. It can be color feature, it can be texture feature, it can be statistical feature like GLCM, nowadays local binary pattern, that can also be used to extract features from the image. Histogram of gradients can be used to extract the feature. If we have so many features, your classifier will be burdened. In order to reduce the burden of the classifier, we have to reduce the number of feature set, that we call it as the dimensionality reduction. Through dimensionality reduction, is it possible to take appropriate feature or unique feature to go for the classification? So there are so many types of classifiers available, like you have random forest, SVM, all those classifiers are there, which has the ability to convert the feature into a particular label, which can be either normal or abnormal. So you can see this here. So this is the fundus image. We are extracting the 3 channels of the retinal image. Mostly green channel will be preferred when compared to other channels. Then how we can do the segmentation in order to go for the optic cup to optic disc segmentation, OD-OC. OD stands for optic disc, OC stands for optic cup. Cup to disc ratio. This can be taken as one of the important feature for the detection of glaucoma. So optic cup and optic disc, how to extract these two from the given fundus image. So that we call it as the segmentation. You can see how results varies because of different algorithms. So here this is your original fundus image. This is after pre-processing. So after blood vessel segmentation, now your job is to get this part, optic cup and optic disc, And from the cup to disc ratio, is it possible to say whether there is a possibility of occurrence of glaucoma or not? These are all the visual analysis of the proposed scheme. So many algorithms can be tried here, like your k-means algorithm, which comes under the category of unsupervised learning. So many thresholding techniques are possible. Either you can go for hard thresholding, soft thresholding, wavelet based thresholding. So if you can extract the feature from the image, that feature, if you are giving it to a classifier, that classifier is able to classify the nature of the disease, then it becomes machine learning problem. On the other hand, if you are equipping your computer in such a way that the computer automatically detects or extracts the features from the input image and it performs the classification, then it becomes the deep learning problem. So here we have done a machine learning algorithm. Whenever you do any kind of an algorithm, we have to be in a position to evaluate the performance of the algorithm. That is done through the confusion matrix. The confusion matrix will result in, as you know, true positive, true negative, false positive, and then false negative. From that, we will be able to get different parameters like accuracy, specificity, sensitivity, and so on, so that we will be able to know whether our algorithm is up to the level or not. This is one study. Now, what is the next study that we have performed in our lab is the grading of the tomato. You know very well the importance of tomato. So tomato can be considered as poor man apple. So widely consumed item. Throughout India, it could be tomato. But unfortunately, this tomato is affected by so many types of diseases. So how to grade the tomato? First of all, I should know whether the tomato being properly ripened or not. Once it is ripened, whether it is of good quality or not. These two things we are supposed to understand. For this, we have used this machine vision and machine learning approach so that automatic grading of tomato, we are able to do it to certain level of accuracy that I will be explaining here. You can see that this is a good tomato without any kind of disease, which is fully ripened. If it is unripe, you can see that green color will be predominant. If it is fully ripened, your orange color will be predominant. But once it is ripened, there is every possibility that this tomato will be affected by different kinds of diseases. The diseases that are predominant in tomato are given here: blotchy, ripening, then sorrow. These are all some names given to different kinds of diseases. So what we have done is we have taken the image, we are doing a pre-processing, then again segmentation, we are extracting the feature. You can see that GLCM feature can be extracted and this can be fed to a classifier in order to understand whether the fruit has been ripened or not. So in order to understand whether the fruit has been ripened or not, color plays a very important role. Color of the tomato. If it is orange, then it is ripened. If it is not orange, if it is green is predominant, then it is unripe. But once it is ripe, naturally there is every possibility that it may be affected by different types of diseases. So which type of disease the tomato belongs to, that also we are interested in. So your machine learning algorithm has the ability to detect whether it is ripened or not, as well as what is the nature of the disease that is present in the given tomato grading and sorting. But if you want to do it in the deep learning approach, major problem what we face is the data set. So you are in need of more number of data to train your network so that it can classify different types of diseases. Nowadays, so many algorithms are there for data augmentation. Either people are now using autoencoders, GAN, and other type of networks. But at that time, we are least exposed to such kind of advanced concept. That is the reason why we have employed machine learning approach for this. Nowadays, because of latest trend in deep learning, you can try with data augmentation technique in order to perform this task so that it will be a boon to the agricultural community. Whether good algorithms, if you develop, naturally it will improve the productivity of the tomato. Indirectly, it will help the agricultural community. So to know the basics of image processing, these are all good resources. for machine learning and deep learning. I'm sure subsequent sessions by eminent professors from Calicut University as well as from other institutions, definitely they will motivate you to get into a proper direction so that you can understand the applications of machine and deep learning in one-dimensional case like speech processing, ECG, and in two-dimensional case like fruit sorting and grading, retinal image analysis. These case studies that I have given as a nutshell. So definitely a lot of database data set is available. You can play with the data and then you can come out with some fruitful algorithm. So if there are any queries, feel free to discuss with me whatever thing that being covered in this topic. If you have any doubt, please feel free to discuss with me. So if there are no queries, let me thank the organizers for giving me the opportunity to discuss with you all. So thank you very much. It's nice talking to you, budding researchers and people who are planning to do research. It's a very good area and try to get as much information as possible in the next sessions so that it will be useful for your further research as well as development. Let me thank the organizer. Let me thank the audience also for patiently listening to the lecture. Thank you very much and have a nice day. Thank you, sir. Shall I leave, sir? Thank you.